What's up, fellas? It's Everything and More, the podcast in which we talk about everything and more. So, in today's episode, we're going to be talking about one of my favorite topics: general and special relativity. These are two topics that are extremely hard to understand, but I'm going to do my best to break it down so you, your brother, or whoever may be able to understand and can actually appreciate it because it's really interesting and it's fun too. So another quick drinking game we're gonna play here. You play it if you want to or not, and it's every time I say the word relative or some form of that word, take a shot. God bless you if you decide to play this game, fellas. You're gonna be really drunk. Anyways, so you guys ever wanted to see what the future will be like if artificial intelligence will have taken over the planet, if interdimensional travel as seen on Rick and Morty will be possible, if teleportation will be possible? As of now, we can only teleport single atoms, which is actually pretty cool. I might talk about that in a future podcast. Will time travel be possible? Stick around, I'll let you know how you can do this with science. No, I'm not kidding, it's actually possible. Small print, just highly improbable. So technically, with the technology we have right now, it's impossible, but it's also possible. Anyways, first, I'm going to give you a quick basic introduction to light. So understanding light is crucial for understanding special and general relativity. So when first talking about relativity, we must first discuss that light actually has a finite speed, which was an amazing discovery when it was discovered. We'll talk about more of that later. So what does that mean? It means when you turn on your flashlight or your phone or whatever, it may look like the light from the device to wherever you're pointing, it gets there instantaneously, but it actually takes time for the light to get from your flashlight to wherever you're pointing. This is known as the speed of light, aka the universal speed limit. So in physics class, we saw this number as 300,000 kilometers per second. In more conventional terms, 670 million miles per hour. That is so fast. Let me look at the speed of sound real quick, just to tell you guys right now. Let's see. Speed of sound in miles per hour. Speed of sound in miles per hour is 767 miles per hour. That's it. Well, not that's it, but relative to the speed of light, that is so minuscule. And it takes so much energy and effort to break the sound barrier. Imagine breaking the light barrier, which is actually impossible. But going like half of the speed of light, or even like 1,000th of the speed of light, we'd have to put so much energy. It's, oh my god, it's like what, a million times faster than the speed of sound. It's crazy, fellas. It's so fast that it looks instantaneous to us, but it's not. So the first person who actually discovered that light has a very fast yet finite speed, I'm gonna butcher his name, is O. Christensen Romer, a Danish astronomer. And he found this out in 1676. He realized that the amount of times at which moons of Jupiter appeared to pass behind Jupiter were not evenly spaced. So Romer saw that the eclipse of Jupiter's moon appeared later on Earth the further away we were from Jupiter. What does this mean? That means the further away we were from Jupiter, the longer it took the light to reach us, meaning that the light from the moons took longer to reach Earth because we were further away, proving that there is a finite speed of light even though it's not completely obvious in our day-to-day observations. So the next piece of the puzzle that troubled physicists was what medium light propagate through. So this might sound complex, but it's not. Let's discuss it real quick. First off, sound waves propagate through air, correct? Or they travel through air. Therefore, there's no air around us. You can't hear this podcast. In space, you can't hear each other talk. But, astronauts can talk to each other and talk to NASA back on Earth or whatever, because they're in a vacuum with air. So their waves can propagate through that. But if there's no medium for the sound waves to propagate through or travel through, you won't hear anything. Or something more tangible would be ripples in a pond. The waves propagate through water, right? So therefore, scientists thought that light should travel in a medium just like all other waves. They called this theoretical medium ether, something that was present everywhere and always, even in space. But now we know that's baloney. Space is completely empty, and that light does not need a medium to travel through. And now that we got that cleared up, let's talk about frames a little bit and the speed at which one another views light. So let's start off with a basic example. So if I throw a ball at your face at 50 miles per hour and you're running towards me at 10 miles per hour, the ball is going to hit you in the face at 60 miles per hour, but leave my hand at 50 miles per hour, right? The speeds add up for you and they stay the same for me. If you're running away from me at 10 miles per hour and I throw it 50, the ball's going to hit you in the face at 40 miles per hour. Why am I throwing it at your face? I don't know. This is just for analytical purposes. Therefore, the same exact logic should apply to light, right? Which was supposed to be the whole point of ether. The speed of light moves relative to the ether, but the speed of light remains the same relative to the ether or to whoever. It remains constant no matter if you're going towards it, away from it, or you're stationary. So we're not going to get too in depth, but in 1887, an experiment carried out by Albert Michelson and Edward Morley, also known as the Michelson-Morley experiment, found out that the speed of light is actually always the same, no matter the frame. And now this is where it gets good, and it starts to get a little bit more interesting. In 1905, a famous paper was published by an unknown clerk in a Swiss patent office. Can you guess who? I'll give you 5 seconds. 5, 4, Albert Einstein. You gotta be quick on your feet. Albert Einstein in 1905 published a paper, and what he said was that the whole idea of ether was pointless if you throw out the notion of an absolute time and space. For all you nerds out there, the principle of relativity states that the laws of physics must be the same in all inertial frames. So let's talk about special relativity. So to first understand special relativity, we have to first state that the distance between 2 points and time interval between 2 events is relative. How crazy is that? It seems like it's absolute, right? It's the same for everyone. So this means that both space and time are both relative, and each depend on the frame of reference, aka who, in which they're being measured in. In normal terms, space and time depends on who is looking at what and where they are and how fast they're going. To dumb it down even further, it's all in the eye of the beholder, which is crazy because we know beauty's in the eye of the beholder, right? Because beauty's subjective. Everybody has their own standard of beauty. And you think, oh, physics is clearly objective, right? But no, when it comes to relativity, it's subjective, meaning it depends on the subject measuring it. But the principles are objective. That's important to note. But the outcome is subjective. So that's crazy to think about it when you put it down like that. I think it's very interesting. So let's start off with the concept of time dilation. Running clocks move slow. So let's explain this whole time is slower for someone who is moving. All right, so every day we just think of space and where we are going, how we are getting there, and so on. But we live in space-time. There is space and time. So when you tell somebody, meet me in the east end of Golden Gate Bridge, whatever, wherever you want to meet them, you're not just going to tell them where to meet you. You're going to tell them when to meet you. Meet me at the east end of Golden Gate Bridge at 9 p.m. on Saturday. So let's make knowing that, let's make an analogy real quick. Imagine I'm driving a car on a straightaway track of 10 miles. I'm driving this car at 100 miles per hour. Therefore, for me to finish, it should take 6 minutes. My friend's timing me. After every run, I take a shot because I'm a fun guy and I'm an alcoholic. I'm actually not. It's just for the purpose of the story. So let's recap again real quick. I'm driving on a straightaway track of 10 miles. I'm driving at 100 miles per hour. So it should take me 6 minutes to finish. So the first run actually takes me 6 minutes. And then I take a shot of Hennessy because I like it. The second run takes 6.5 minutes, and then I take another shot of Hennessy because I like it. And then the third run takes 7 minutes. So the first run took 6 minutes, took a shot. Second run took 6.5 minutes, I took a shot. And the third run took 7 minutes. And then I start questioning myself, why am I taking longer? And my friend explained it perfectly to me. He says, well, Guy, which is my name, well, Guy, each time you take a shot, you are no longer driving in a straight line, but a tilted line. So the distance you have to travel is further. Keeping in mind, we travel at the same speed of 100 miles per hour in all runs. And this makes sense because instead of just driving in one dimension, east and west, I was now starting to drive in another dimension, north and south. So now part of my speed is not only used for traveling east and west, left and right, but also some of that is diverted into the north and south. up and down, right? So I'm not driving in a straight line, I'm driving in a slope line. So the distance I'm covering is longer. So it's going to take me longer. Duh. So keeping this in mind, not only do spatial dimensions share an object's speed, but also time. Crazy to think about that, huh? Therefore, this fixed speed can be shared not only in the space dimension, like the driving car example, but also in the time dimension. So the faster an object moves through space, the more motion through time must be diverted. This implies that the object moving through space and time will travel more slowly through space than its stationary counterparts. So what does this mean? Well, it means that if the faster you're traveling through space, the shorter your time is going to be relative to other people. Right? This is the weird part. For you, you're going to experience the same time, 1, 2, 3, 4, but somebody outside of your frame, if you're going fast enough, for them you're going to be going 1, 2. It's weird. Running clocks move slow. So if you're going fast enough, and when I say if you're going fast enough, this only becomes apparent when you're going like 14% of the speed of light, which is extremely fast. 10% of the speed of light. So that's what? 67 million miles per hour. Like, we can't achieve that. No way. Somebody our way. I mean, we can do that in like particle accelerators and stuff. They actually have to take this stuff into consideration because they're accelerating particles into significant speeds of light, like Stanford Particle Accelerator. But we're not going to be talking much about that. But knowing, like, theoretically, it's possible. But when you take into account humans and how heavy we are and how much energy this would take, it'd be almost impossible. So, next I want to explain a little fun paradox. So, I mean, when you talk about relativity, it's full of paradoxes. First one that we're going to discuss is the twin paradox. So the twin paradox is there's two twins. You have twin A, we'll call him Guy, and you have twin B, we'll call him Gus. Guy and Gus, I'm Guy, my brother's Gus. We're not twins, but for this example, we're twins. So I live in planet A, and so does my brother, my twin brother, Gus. And he's traveling to a far distant planet dozens of light years away. So a light year, if you guys don't know, imagine turning on your flashlight and that light travels for a whole year. That's how far a light year is, right? So if you want to find out how far a light year is, you just travel, or you just multiply the speed of light times 365 days, and you get a light year. That's really far, by the way, extremely far. And so he's traveling. He's going at a significant pace. He's going at about, let's say, 80% the speed of light. And so when he comes back, he says, Guy. Because, right, he goes to the planet and he comes back, and he was going at a really fast pace. So one of us should be older than the other. We're no longer twins. We were born twins, but now we're no longer twins. And so we talk to each other and we try to decide who's older and who's not. My brother argues that I'm older. Oh, shit. Hold up. So my brother argues this. Look, Guy, I was still the whole time. The distance between the two planets were shrinking, increasing. So I was still. So since you were moving further and away relative to me, your clock was moving slower. And I said, no, Gus, your clock was moving slower because you're the one who is driving away and towards me. So now you got to ask yourself, who's right? Who's older and who's younger? Well, the answer is I'm right. Because relative to my brother, I did not accelerate. I didn't experience a change in acceleration. I was constant the whole time. My brother's the one who felt the force, right? Because imagine if you're in a train and you can't see outside. The train is completely shut and it's moving at a constant velocity. It's impossible. It's physically impossible for you to tell if the train is moving or not. This is true. But the second the train starts to accelerate even in a little bit, or it hits bumps on the roads, now obviously you're going to be able to tell if you're moving or not. And you know, this happens sometimes if you've ever taken the train and like you're sleeping, all of a sudden you wake up and there's a train next to you. All of a sudden the train's moving, or your train's moving for a quick second. You can't tell which train is moving. So kind of the same principle starts here. So since my brother accelerated and decelerated, or sped up and slowed down, physicists don't like using decelerated, whatever, I'm right. So therefore my brother is a lot younger than I am because his clock moved really slow. So for all I know, depending on how far the planet is, he could have, like, I'm 25 right now, right? And let's say my brother's 25 too, because we're twins, or we were. My brother could have aged. Let's say his trip took 5 years for him. He could have aged 5 years, and for all I know, I could be he's 30 years old, and I could be like 200. Right? It's crazy. Like, that's actually possible. And we'll talk about some of that math in Interstellar, the movie, once we talk about general relativity. And I'll mention their spoiler. There will be spoiler. I'm assuming everybody's watched Interstellar because it's a great movie. But if not, I'll warn you. So the next concept of special relativity is Lorentz contraction. Moving objects appear shorter. Yes, guys. The measured distance between 2 points along with time also depends on the observer. Everything is relative. You know that Oprah meme when she says, you get something, we all get something. It's like that, except everything's relative, because it is. It just doesn't seem so in our day-to-day life because it's so minuscule compared. But yeah, even the distance between 2 points and the length of which we measure depends on who's doing the measuring. So let's talk about another paradox. It's called the pole in the barn paradox. It's extremely confusing. So the whole thing is like this. I'm running. I'm a really fast runner, road class runner. I can run up to 75% of the speed of light, and I'm holding a 15-meter long pole, and I'm gonna go through this barn door. And the barn is 10 meters long, and so once I get perfectly inside the barn, once I get in the middle, the front and the back door will close, and when, like, the second I get out, it'll open, or the second I fit in. So it opens and closes pretty much at the same time. The second I'm in there, so I get in and I get out. And not only that, but my friend is looking outside, and we're gonna compare each other's viewpoints. And so I do the whole run, and it works. And what my friend says is like, Guy, here's what I saw. What I noticed is I'm really good at measuring things, and I noticed that the pole you were carrying shrunk from 15 meters to 9.9 meters. And the barn door is 10 meters long. Therefore, right when you got in the middle, I opened and closed the door so you can go out. And I said, hold up, that's BS, because the way I saw it, the barn door size, the barn length shrunk from 10 meters to 6.6 meters because that was standing still. The pole relative to me wasn't moving. Right? It's kind of like when you're in a car, everything in the car is pretty much still, except when somebody's outside watching the car, everything is moving in the car. Same principle applies here. So I'm holding the pole, and I'm standing still. What I saw was the barn, whatever, god damn it. The barn shrunk from 10 to 6.6 meters. So I'm like, how does this even work out? And then this is the weird part. The resolution of this paradox lies in the relativity of simultaneity. Things happening simultaneously are relative as well. That's the crazy part. So my friend saw the doors open and close simultaneously. I didn't see that. I saw the front door open first, and then I went through, and then the back door opened, I went through, and then the front door closed, and then as I left, the back door closed. It's crazy to think about it like that, but even simultaneously, things happen in a subjective way once you're going fast enough. It's crazy to think about that. And so now that we've pretty much destroyed your brains with special relativity, let's destroy it even further with general relativity. So Einstein, the godfather of relativity, special and general, realized that special relativity and Newtonian gravity did not agree with one another. So what does that mean? According to Newtonian gravity, right, Isaac Newton, if the sun were to blow up, we would feel the effects instantly. But that's BS, because nothing travels faster than the speed of light, right? Because if we were to feel it instantly, the light of the sun to reach us would have to travel instantaneously, infinite miles per hour, but it doesn't. It travels at 670 million miles per hour. So, what does this mean? It means that's BS. And Isaac Newton knew this. It was something that he lived with, and he knew he was wrong in that term. But, once you're working with day-to-day terms, it's not really that big of a deal. So, Einstein created a new theory called general relativity. So I'll link a video on my YouTube description that describes this perfectly, and I'll link one too with the barn door paradox, and one that explains it perfectly, and maybe the twins paradox. So if you're listening to this, just go on my YouTube and look at this episode, and just look at the descriptions. There's some really really good videos that describe it if you're more interested in it. So imagine, you've probably seen this too. Imagine space-time as a fabric, and anything that has mass and energy creates, right? Because E equals mc squared. Mass is energy. So anything that has mass creates a warp in this fabric of space-time. And gravity is a consequence of this warp in the fabric of space-time created by energy and mass alike. This warp even causes light to bend when it's near strong enough gravitational fields. Not only that, but time should appear to run slower near a massive body. That's the whole point of gravity. Gravity is just a warp in this space-time. So think about it like this. A sumo wrestler is going to create a larger warp in space-time than I am. But, because a sumo wrestler is way bigger than I am. He has more mass, or she has more mass than I do. But this warp in space-time is so insignificant compared to like the Earth, the Sun, other stars, moons, and stuff like that, that it just doesn't even matter. It's minuscule. But once you start reaching a mass of heavenly bodies, right, these huge bodies such as stars, sun, then you really start feeling the gravitational effects. And sun feels our gravitational effects, and we feel sun's gravitational effects much more, and it's all due to this warp in space-time, this fabric of space-time. It's so cool. You can search some videos on YouTube that they have some great what am I looking for? Some great demonstrations of how this works. Obviously, it's not perfect because in the demonstrations there's gravity. So like the balls, you'll see what I'm saying. Okay, just look it up, dude. Anyways, there's actually been experiments done on this, and so they look at a clock tower and they put a clock up high on the clock tower and they put a clock down low. And so what happens? The clocks when the experiment's done are going to have different times. Why? Because one clock is higher away from, Earth's gravitational pull than the one down lower. So the one down lower is going to go at a much slower pace. Not much slower. It's going to go slightly slower than the one up higher. Right? And here, I'm going to read a quote from, what book is this? A Brief History of Time. It's from Stephen Hawking, R.I.P. And it's an amazing book. It's actually a really simple book for you guys to read. Like, you don't have to know anything about physics to appreciate it. And here, I'll read the quote, and he sums it up perfectly. Another prediction of general relativity is the time should appear to run slower near a massive body. As light travels upward in the Earth's gravitational field, it loses energy, and so the frequency goes down. This means that the length of time between one wave crest and the next goes up. That makes sense, guys? The closer you are to something, the closer you are to a large body, the more of a pull you're going to feel towards it. Therefore, your time's going to slow down. And, relative to somebody further away from that pull. So, and this is seen also in Interstellar. In Interstellar, you see this mapped perfectly. The hardest point. All right, here's spoiler alert. In Interstellar, there's something wrong going on with planet Earth, right? There's like this whole Earth is messed up. There's dirt everywhere, and they're trying to find another planet to live on. And so they gather these astronauts and they send them far off. They send them through a wormhole, and they're searching for planets where they can start new life and new civilization. And so the thing is, they're trying to save the people who are on Earth right now. Well, I mean, it's a little bit more complicated than that. You watch the movie, they're also trying to start a new life, and while people on Earth go extinct. But the whole point of the movie is they're trying to save the people on Earth while this whole mess is going down on Earth, right? And so, but there's a problem. The problem is when Matthew McConaughey, I don't know his name on Interstellar, Anyways, the problem is when he is looking for a planet, he he has to decide really carefully where he's gonna go, because certain planets he's gonna age extremely slowly compared to people on Earth. Meaning that if he stays a couple of minutes and a couple of hours on a certain planet, that could result in decades on planet Earth. And so, but he's trying to get this done quick, and so the whole predicament is, oh my God, we gotta get this done fast, and we gotta pick a planet where we won't age too slowly relative to people on Earth, and we gotta age the same, because they were near a massive, massive black hole, and he felt his time being slowed down because the gravitational pull from that black hole was so strong and it was so massive. And I'll talk more about black holes in another podcast and how black holes similarly resemble the Big Bang. We'll talk about that. It's really interesting, actually. And but that was the whole point of the movie, is that, oh my God, this general relativity is gonna fudge us in the buttocks. Because if we stay here for too long, 1 year here could be like over a century on planet Earth. So we gotta do this fast, and we gotta do it now. And not only in movies is it applicable, but also in your day-to-day life. So now you're thinking, Guy, how does this general relativity thing apply to me in my day-to-day life? Well, I'll tell you this right now. There wouldn't be such thing as Uber and Lyft without it. And you're asking yourself, what the heck do you mean there wouldn't be Uber and Lyft without general relativity? Well, GPS has to take into account the difference in gravitational pulls from, because we're closer to Earth's gravitational pull, whereas the satellites are further away. And so general relativity has to take that into account, or else the signals we would be receiving from satellites would be way too, well, let's see, would it be late or early? Because we're feeling a stronger gravitational pull, therefore our time is going down slower. So we would be receiving these signals faster than we should. Therefore, if we'd be taking a left on Alameda de las Bugas or wherever way earlier than we should, and the GPS, it just wouldn't work. So GPS has to take into account for general relativity, right? So this isn't just a crazy thought experiment that we're doing. This is something that happens in your day-to-day life. Even with special relativity and particle accelerators, they have to take that into account. And not only that, but if we're going to travel into Mars, you think Elon Musk doesn't know anything about general relativity? I'm sure he's well immersed in the topic. And even NASA did an experiment. NASA did an experiment when you might have heard this. This was a famous experiment recently just done, where they sent out a twin on space station for 1 year. And he stayed there for a whole year. He was messing around doing these experiments, but whatever. But the whole point of the experiment was to see how he would change relative to his twin on Earth, which was a retired astronaut. And so he came back, and not much has changed, except his gene expression. They call this the space gene. 7% of his gene expression changed. And don't even ask me what gene expression is. I'm not a biologist. All I know is 7% of that gene changed. And that's due to the effects of general relativity and how gravitational pull was stronger for the twin here on Earth, where it was lighter for him out there on space. Not only that, but he lost muscle and other stuff, right? Because when astronauts go into space, they actually have to exercise daily, or else they will become very, very weak, right? Imagine you're going to the gym and you're lifting, everything you're lifting is all of a sudden 100 times lighter. That's how it is being an astronaut, pretty much. You use a lot less of your muscles. So they did this whole experiment just to look at the effects that general relativity have on twins, on space travel, and general relativity is important in even our day-to-day lives, as we just explained. GPS. Let's see, where else will you use space general relativity? I'm assuming maybe airplanes when they're communicating with one another. That might be a slight. They might have to slightly take into account general relativity. I'm not sure, but pretty much it's in our day-to-day lives, and it's very important. And if we ever want to do space travel and we want to get really good at it in future generations, it's definitely something we'll have to take into account. So guys, this was an extremely fun episode for me to research. I really miss this stuff. I took a whole class on this stuff on college, and I miss it. I had a lot of fun bringing it to you guys. I hope I did my best to really dumb it down for you guys, so you guys can understand that. Remember, running clocks move slow, and that's because the faster you move through space, the more speed has to be diverted from time to space, and so therefore your clock's gonna slow down. Same principle with length, right? And then the closer you are to a large body, that creates a larger ripple in space and time. Therefore, it's going to slow your time down even more relative to somebody outside, right? So those are pretty much the principles of relativity. And I hope I did my best to dumb it down for you guys, and you guys had fun listening to this podcast. If you have any questions at all, which I'm assuming you do, and you want to talk about something, you have ideas for future podcasts or anything at all, shoot me a DM, slide into the DMs, ENM podcast on Instagram or Twitter too. Everything and more, ENM podcast at Instagram. And I honestly can't wait to bring you guys the next episode. I'm having a lot of fun doing this. Hope you guys can tell. Hope you guys are doing the same, honestly. It's so much fun. Anyways, guys, till next time, peace.